So, notice I've added some things to the paper here. I've looked up properties of air at 60 degrees Fahrenheit, 1 atmosphere. I've got some properties here. Where do I find that? Back to your textbook. Here I've got properties of air at 1 atmosphere, and I do have a row for 60. So I just looked those properties up. Okay. You pull those off. Our text is reflecting about 0.07633 pound mass per cubic feet. I assume if you took about 1.2 kilograms per cubic meters and converted that to English, you should get something very close to that. I went ahead and pulled the viscosity. Why would I want the viscosity value? Any suggestions why I would want the viscosity value? Okay, well, if you know, you can say it out loud. I don't know if anybody's around you. Maybe they think you're crazy for yelling at your computer screen or your phone. But anyway, we'll see why we need that in just a second. All right. Okay, so I've got properties of air now. What else do I need? So I've got densities, I've got the speed, I've got the areas. I need the coefficient of drag for the sign and for the rod. And then I think we should be set. Okay? All right. So I'll set that to the side there. What else we got? So I need to go find those drag coefficients. All right. Back to the textbook. Okay. So let's start with the sign here. Ooh. Sorry. So I start with the sign here. Let's see. You're going to hear a pop. I want to see if I'm on the screen or not. No, I was not. This one. All right, you see this one? I got a rectangular plate, area length times this d, the height there. It says the coefficient of drag for that guy is going to be this based on this expression, and that's for this range here. So we're in that range. Now, one thing to mention, remember back up at the very top here, this is said for Reynolds numbers, very, very high Reynolds numbers. Do we have a very high Reynolds number? Yeah, I think so. But good news is we got that viscosity value. So, yeah, I think we can figure that out, right? So as long as I have a very high Reynolds number, coefficient of drag for the sign, we can approximate as a rectangular plate. What you do is you just look in these tables and see, can you find one that closely describes your situation? That's 1.10 plus, this one's based on the equation. Most of them are not based on the equation, they just give you a value. This one's based on equation. So 1.10 plus 0.02 times the ratio of the dimensions, L over D, plus the ratio, the inverse ratio, the other ratio of those dimensions. So that's the expression they use here, and that we are within the range for that one, assuming our Reynolds number is good. So we need to check our Reynolds number. This is for a turbulent flow. Now, there is on this previous page here, they said that I've got a circular rod. That's what I have. I have a circular rod. And they've given me two different numbers here. They say if it's laminar, use 1.2. If it's turbulent, use 0.3. I'm betting we're turbulent, but we really need to make sure here. Okay? So, if it's turbulent, coefficient of drag for the rod is going to be 0.3 if it's turbulent. Right, and they're suggesting for external flow, for these they're suggesting a Reynolds number greater than 10 to the 4. Okay, so let's see. I'm betting we're way past that. Let's just make sure. So let's look at the Reynolds number for the sign. Right, that's going to be, they're both going to be rho v and a characteristic length divided by mu. Okay. All right. Well, you can write these out. I'm going to kind of try to save us a little time here. You guys understand our speed here is 100 feet per second. Our density is given down here, 0.07633 pound mass per cubic feet. Okay. And characteristic length, I'm just going to use 10 feet. Right. This is not like a hydraulic diameter. So you just use a length that best describes the object you're dealing with. I would suggest 10 feet is going to be Okay, for this one, I would suggest 1 foot for the rod. The diameter of the rod is what we'll use for the rod, but here we're talking about the size. We'll use 10 feet as the length, and I've got my viscosity value down here. So I'm just going to run those through. Those units are going to, you can triple check that, but those units look like they're going to cancel out just fine. So density, we said, is 0.07633. Multiplied by speed is going to be 100. Okay. And the length is going to be 10. And divided by this viscosity, 1.212. And that is so small. This is e to the minus 5. Yeah, so about 6.3 million is our Reynolds number for about 6.3 times 10 to the 6. We're good there. All right, this one's turbulent. Let's talk about the Reynolds number for the rod, just to make sure. It should be the same story. Rho V D over mu. And here we're using 10 feet as my length for the sine. Here we're going to use 1 foot. Notice everything else is the same. Rho, V, mu, they're all the same. So I'm just decreasing by a factor of 10. So this should be probably 6.3 times 10 to the 5. You could double check those numbers, right? Your density, speed, divide by the mu and multiply by 1, and you should probably get 6.3 times 10 to the 5 roughly. In either case, you're going to get a turbulent value. But, again, the point there is check. You don't know until you check. Right? Yes, you could look at that viscosity value and say, Steve, air is so non-viscous that it's probably going to be turbulent. And I would probably agree with you, but we checked it. Okay. How does that help us? Well, it tells us we've got turbulent flow. So both of these, this was for turbulent flow and this is for turbulent flow. So we're okay. So I've got now my coefficient of drags. I've gone and looked up density. I know the speed. I've figured out my areas. I know the area of the rod, the area of the sine. Good. Now it's just units. Engineering work is done, so to speak. Now it's just algebra and units, which is the hard points to get, if you will. But the way I grade, I try to get you to 80% of the points at this point if you show me, what to use and how you're going to use it. So let's start plugging numbers in. So I'm going to set my tablet aside. I think we're good for now with that. Let's set this next to us here, and let's just get to crunching, shall we? So the drag force on the sine, 1/2 coefficient of drag for the sine. Oh, goodness, let's, well, this is 1 and this is 1, right? This is 10 by 10 plus 10 by 10, so this is 2. So this is 0.02 times 2. This is 0.04, so this is going to be 1.14. Does that make sense? 1 makes 2. 2 times this, 1.14. So our coefficient of drag for the sine is 1.14. Density of the air we've got down here, we said, is 0.07633 pound mass per cubic foot. The speed squared, it's moving at a brisk 100 foot per second squared. And the area of the sine, we said, is 100 square foot. Okay, let's get a number and worry about units in a second. So if we get a number, I've got, let's say 0.5 times 1.14 times 0.07633 times 100. I could cube it. We'll just square it, and then times another 100. Okay, that's a big number, but the units don't make sense yet. That is 43,508, if you want to keep that many digits. I've got feet to the 4th on top, feet cubed on bottom. This is pound mass. I've got a foot on top, and then I've got per second squared on the bottom. That is not force, but that is mass times distance divided by time squared. So I should be able to convert that to unit of force. And recall, by definition of a pound force, 1 pound force times second squared is the same as 32.2 pound mass feet. So divide that by 32.2. 1,351 pound force. It's a lot. Maybe this thing can hold it. I don't know. We don't know what this thing's made out of, and I'm not a materials guy. I'm just a fluid and thermo guy. So we'll leave that to either we'll brush up on the other stuff, or we'll leave it to somebody else to tell us whether that can work or not. Okay, how are we on time? 4 minutes. We're good. All right, let's go find drag force on the rod. That's going to be 1/2 times the drag coefficient, right? Again, where am I getting this? Back over here. Drag force on the rod, 1/2 coefficient of drag for the rod, V squared area of the rod, okay? Coefficient drag for the rod, we said 0.3. The density is the same. It's the same air flowing over it, so it's 0.07633 pound mass per cubic foot. The same speed, 100 foot per second. That's going to get squared because V gets squared. Times the area, we said that is a 60 square foot projection facing into it. Okay? Over here, area of the rod, the 60 foot length times the 1 foot diameter, 60 foot squared. And we know we're going to need this conversion factor to get a number that makes sense, so we'll go ahead and apply that 1 pound force second squared is the same as 32.2 pound mass feet. And we'll run those numbers. 0.5 times 0.3 times 0.07633 times 100 squared times 60 divided by 32.2. Much smaller. It's not a lot of, a little less area, and it's also a smoother surface. So, force drag on the rod, 213.3 pound force. Again, why is it so much less? Well, look at your drag coefficient. A big square profile, bigger drag coefficient. A smooth, rounded surface, the air is able to move over that surface, right? Right? If I've got air trying to get past this, as opposed to trying to get past this, you see why the drag coefficient is so much bigger for this one than it is for this one. It's easier for that air to flow around it. Can't really flow around this nearly as easy, so a bigger drag coefficient on the sign, so a bigger force. Not a whole lot of difference in the area, but a bigger drag coefficient means bigger drag force. Okay, are we done? No. The problem wanted to know what is the maximum moment. We got to help the material guys out to see if this thing can withstand it. So we go back over here, right? And if we look at this free body diagram over here, we say, well, the moment about point A, that reaction moment about point A, is going to counteract these drag forces. So that's going to be the drag force of the rod times 30 foot to get from A to the drag force of the rod, right, from here to here. And then from here to here is 65 foot. So it's plus the drag force on the sign times 65 feet. Right? Now I've got those numbers all here, so let's just run them out because I'm a little short on time. Try to get this in before my 15-minute break. 213.3, that's the rod, 213.3 times that 30 foot, right? That is 6,399 pound force feet. The other one is 1,351 times, and that's 65 foot from point A. So that is 87,815 pound force feet. Add to that this other 6,399. Okay, thanks. 88,000, we'll say 500 pound force feet. That's your maximum moment. I gotta stop there. Cloud pop. Perfect. See you guys.